Welcome in EE-341 linear control system. It's the lecture number 29, and so far our major topic is steady state error. How to find the steady state error? It is already drive, and we discuss in detail in last two lectures. So difference between the input and output at time equal to infinite is the steady state error. Our main topic of this lecture will be to study the impact of steady state errors, how we can use, especially in designing part, and then another specific topic where we cover the and find the steady state error for disturbances. And next topic is to find the steady state error for non-unity feedback systems, and definitely we combine these two topics, and there will be another topic. And the last topic of this lecture will be to find the steady state error if the systems is represented in state space. And starting from the review of CLOs related to the lecture, and definitions, and some basic formulas of steady state error, and review the part of unity feedback systems, and relevant to the steady state error. And most important part which will be helpful in this lecture is the static error constants and their type of the systems on which depends the steady state error, and how this is affect by these two factors, and by the input and the type of the systems is already covered, but we will try to review the few part of in this lecture. Analysis uh, part is mostly under the discussion of transit analysis and stability and the steady state errors. And ultimate our goal in this course is to design a robust systems which is error free, and it is according to the our requirement, and it is also economically and socially considerable with these considerations. So CLO2 we are considering here to discuss the steady state error. So steady state error in terms of if the closed loop transfer function T of S is given, and with the input is R of S, and its response is C of S, and then E of S representing the difference between the input and output, and this is defined through this relation. This is the error signals are the error. And if we want to find the error in steady state at time equal to 0, then by applying the final value theorem, and ultimately we have this relation in terms of steady state error, and in terms of closed loop transfer function. But in terms of open loop transfer function g of s, when we apply the some reference value, and there is some output response of s, and e of s is representing the difference between the input and output, because here we considering the unity feedback, so it is directly equal to the difference between the input and output. But if we consider the non-unity feedback systems, then definitely the relation will be different. So we drive the error signal in a closed loop unity feedback systems, which is E of S equal to input over 1 plus G of S. If we take this value in this one and apply the final value theorem, then we can find the steady state error. Both type of information is, if given closed loop or open loop transfer function, then we can find the steady state error. There are some static error coefficients, for example position constants, which is kp. It is equal to g of s when we applied the limit s approaches to 0. It gives the dc gain, uh, and if we take the derivative of this one, and it is equal to s times g of s, and it by applying the initial conditions, then it gives the velocity constant. And similarly, if further we take the derivative in s domain, then we can by applying the initial conditions, then we can find the acceleration constants. And the corresponding steady state errors, if the position constant is given, then steady state error is equal to 1 over 1 plus position constant. But keep in mind, in this case we have input is step, and similarly if if the velocity constant is given, then just to find the steady state error, just take the reciprocal of this one, this constant, then we can find the error constants. And in this case input is RAM, and similarly for the third case, if the acceleration constant is given, then taking the reciprocal of this one, and we find the steady state error with the parabolic input. So all the discussion here of the system, if the system is stable, and uh, from this table we can comparing the type 0, type 1 and type 2 system. Definitely type 2 systems is more suitable, and it is prone to the errors if it is stable, but definitely there are some drawbacks if we have the two pole at the origin, and how to compensate it. It definitely, but it is very important. It will I will try to review this part, this term, in the next slide. For example, this is open loop transfer function g of s, which is type 0 systems. Um, for impulse response, its error is 0. But definitely if we apply the step, RAM and parabolic inputs, and especially in RAM and parabolic inputs, the steady state error is undefined. So it is not preferable type 0 systems, and but if we increase the type, it means if we here taking the s maybe power 1 or 2, it means there are the two poles at the origin in a complex plane. And if we consider this type of concept in time domain, it means there is in time domain there is some t raised to power cubic and some coefficient here, and if we apply time approaches to 0, so definitely its effect will be considerable, and it deviate from the results, and this thing make the systems unstable, and in this case steady state error is infinite. For type 0 systems, for example, if we take the inverse Laplace transform of this one, and try to plot this one, and if we see, if we observe that blue color is the input, and red is the response, and this part is the transient part, and this transient part definitely varies accordingly, and ultimately steady state result is matches to the input. And if there are time, there is t multiplying here in time domain, then this thing uh, in time domain, if we consider the limit at time approaches to infinite, then this result make the disturbances here, and makes the errors. So steady state error and the transient analysis. And we see that transient response of the in a control systems, actually it is specified, and definitely it varies, and response will be changed accordingly with the damping ratio, settling time, and the peak time and percentage overshoot. If we are considering the transient analysis, then these parameters definitely important. And if we consider the steady state error, then there is some specific parameters which are the some static constants. Here the position constants and the velocity constant and acceleration are constants. As these definitions are derived here, and this is in detail in last two lectures. Okay, up to here we are finding these values. In a reverse way, if the position constant is given, what is mean by that? If the position constant is given, similarly if the velocity constant is given, if the acceleration constant is given, and if especially if we want to achieve some percentage or in a specific way, how to these topics related to the steady state errors. Let's see in the examples. For example, if the velocity constant is given, it means velocity constant is 1000 is given. It means first of all we can guess here the system is stable, and if the velocity constant is given, then it is definitely it is type 1 system. There is one pole at the origin, and test signal for this situation is the RAM input. If we want to find the steady state error from the given velocity constant parameter, just take the reciprocal of this one. So if the position constant is given Kp, which is equal to 1000, then first of all we can include that system is stable. And for position constant, systems type is 0, and here uh, test signal for this type of system is the step input. And if we want to find the steady state error, if the position constant is given, then this formula is equal to steady state error equal to 1 over 1 plus the position constant. Then we can find through this one. Like in transient analysis, system design parameters are there, and similarly uh, systems performance parameters like in terms of steady state error are the static error constants. If the inputs are specified by the three different type step, inst, ram, and the x and the parabolic, and corresponding coefficients which are the static error constants are the position constant, velocity constant, and the acceleration constants. Here in this example we have to develop a designing part. In this example we have to find the value of k, which is and the steady state error is given, which is at 10%, and the open loop transfer function also given, which is equal to k times 0 at -5, and there are 4 poles. One is at origin and other is at -6, and next is at -7, and similarly fourth one is at -8. So it one pole at the origin, it means it is a type 1 systems, and corresponding to this one error is some have the fixed value, so system is stable. And this shows that and system is type 1 systems, and the corresponding input is the RAM input, and the corresponding error constant is the velocity constant. And the definition of the velocity constant is equal to velocity constant is equal to limit s approaches to 0 as g of s. And the steady state error, from here we can find it is the reciprocal of the velocity constant. So it is 0.1 value, it is because kv is the 10 value. So we can find the value of k where kv is given. So just apply the limit s approaches to 0, and we have k here is 672, which is the value corresponding to the system when it is operated in a steady state within the range of 10%. Now again, a next very important topic related to the steady state error, uh, when there is some unwanted signal is adding in between the controller and plant, and this type of disturbances how affect the steady state error. This is our main topic. Okay, in this diagram we have r of s is the input required value, and e of s representing the error signal. G1s is the transfer function for controller, and similarly G2s representing the plant transfer function. And again we have a unity feedback system h of s, have the transfer function value 1, and there is some disturbance between the controller and plant, and C of S is the controller output value. Usually feedback systems are used to compensate the disturbances are the input are the unwanted type of inputs in the systems. But how will affect the steady state error? Let's see. uh, so in this case C of S, okay, derivation is very important, so try to understand and then individually try to drive this type of relation. And up to here we have no more some difficult derivation, but up to, and the next we have some important derivations which are not the conventional situations, so try to try to understand these. So here we have d of s, which is multiplied with the, and adding here the value is e of s is multiplying with g1s and adding with disturbance d, and whole combination up to here is multiplied with g2s. So this is equal to the c of s according to the block reduction methods. So if we multiply this G2 with the disturbance terms and the some G1 terms and E1 term, so this is the relation we have. And error signal for unity feedback systems is simply difference between the input value and the C of S or output value. From here we can find the C of S in terms of R of S and E of S is equal to R of S minus E of S. So this term is going here and this is here. So this is value. So use this C of S in terms of R of S and E of S, and the above relations become like this one. So by applying the values of this and substitute here, and we have this value. And now this EFS take on the right hand side. So next we have this one, and taking the common EFS in these both terms, and this term is take on the other side of equality. So we have EFS is equal to 1 plus G1 plus G2. So it is equal to R of S minus D of S G2S.
So E of S, here our objective is to find the error signals in terms of the other parameters. So error signal is equal to just dividing by this relation, and separately we have the two terms. So this is the error signals due to the input value, and this is the error signal due to the unwanted disturbance. So this is the steady state error. If the steady state error we find from the previous block diagram, then how to find the steady state error? So what will be the steady state error for this type of systems at time equal to infinite? So yes, we are applying the final value theorem. Just applying the final value theorem, we have in the above relation, just multiply this s in frequency domain here and also in the this terms. So there are two terms which are representing the error in steady states. See, see, both terms are representing the errors which is dependent on the controller value and the plant value, and the again controller value and the plant value, and this is also the plant value. So these transfer function is, if the given in our case or any case, then we can find the steady state error for different type of inputs and different type of disturbances. So first term representing the steady state error due to the input, and this is the similar value we have already, like the steady state error is equal to applying the limit s equals to 0 s r of s and 1 plus g of s. Here g of s is replacing by two product of the two transfer function g1 and g2, one representing the controller and other representing the plant of the systems. So in the last we already find its the value of g. Here g is equal to g1 and g2. It is a similar case, already we discussed in details. And the next term is the steady state value which is dependent on the plant transfer function and the product of plant and controller transfer function. So these both relations are very important, and how to this is with different type of input values. So separately we find the steady state error due to the disturbances. So these disturbances, in if there is some disturbances, then the steady state error, it depends on the values of this one, and this s is due to the final value theorem. And if we take some specific values of this disturbance, then we can find the steady state error correspondingly. For example, if we take the some unit step disturbance like this one, if we take this type of disturbance, then d of s is equal to 1 over s. So this 1 over s is cancelled out with this one, and there is only in the numerator term there is g2s, and if we divide by this g2s here, then we find 1 over g2s plus this g2s is cancelled with this g2, and we have only g1s. So this is very important result. G1s with the limit of s approaches to 0, which is the DC gain of this G1 of this controller, which is some constant value. If we increase this gain with any mean, if we increase the value of this gain, maybe we increase the voltage or current value in electrical circuits, then this steady state error due to the disturbance is definitely reduced. And also it depends on the G2S. If we decrease the value of DC gain of the plant, which is G2S at S approaches to 0, which is the DC value of the plant. If we decrease this value of G2S or increase the value of the DC gain of the controller, then we are reducing the steady state error. Of the original systems, there is R, this is some junction, and there is some controller G1, and again there is some summing junction, and there is a plant G2, and there is a output. And if we take here with the negative sign, and this is with positive sign, this is the error value, and here we're adding disturbance, and this is also adding here, and we are talking about the unity feedback systems. Okay, if we consider this input value is 0, if there is no input, what will happen then? Last time we find our relation is equal to this one, and in this relation, this is the error signal due to this input value, and this is the error signal due to this disturbance. If this input value is 0, then we have this term is equal to 0. If this term is equal to 0, then we have this term, which is equal to this term. And how to implement in a block diagram this relation? It is actually like d of s is the input value, and e of s is in this case is a output which is giving the error signals, and this relation is just like the normal transfer functions are derived in the main subject, in the main part of the course. So G1 is just like the feedback value. Here is feedback value, actually it is the controller, and G2 is the plant, and which is representing just like the open loop transfer function, and this is implementation of this one. So this is the block diagram related to the if we want to find the error signals in terms of disturbance. In this example, we have to find the steady state error. We have to find the steady state error due to the step disturbance. So to find the value of steady state error due to the disturbances, and where disturbance is given equal to 1 over s. If this is given, then directly we can't use this relation as it is last time we tried, and actually we have steady state value limit s approaches to 0 s g2 over 1 plus g1 g2 times the disturbance. So this is the relation, and if the disturbance is 1 over s, then cancel out with this one, and this format also derived by just dividing by the G2, and we find the value of G2S, uh, which is the DC value of the plant, and also G1S is the DC value of the controller, and here we find the negative value in steady state of error. So this negative steady state error, this negative sign shows that this steady state value is higher than the input value. Once again we have to find the value of the steady state error due to the disturbance, and this disturbance is given is a step disturbance. So again same formula, and by using the DC gain of a plant and DC gain of the controller, and we have some values like this one. So these relations also gives the some negative steady state error, and this negative steady state error mean this value after passing through the plant, this disturbance gives the some higher value as compared to the disturbance or input value in this case. Next important topic is related to the non-unity feedback systems. So non-unity feedback systems, here we have a transducer with the transfer function G1S, and G2 is representing the transfer function of controller and the plant, and this H1S representing the feedback transfer function. In this case this is not equal to 1. Then here it is the negative feedback systems, and now our topic is to find the steady state error in this type of systems. So if we take this value from here to here, what happened with this one? It is scaled by this transfer function, and another way this transfer function is multiply this one. So next, this g of s representing the product of transfer function of the transducer. Here g1 is representing the transfer function of the transducer, and G2 representing the combined transfer function of controller and the plant, and H of S representing the scaled value of the original feedback systems, and the actuating signal in this case is E sub A1 in S domain. Here this actuating signal is different from the previous one, which is E sub A in S domain. This is not the error signals, because we define error signal is the difference between input and the output. Here we cannot find the value of output here C of S. It is some like the transfer function times the input value. So it is different from the previous case. If the system is given in non-unity feedback systems, for example, this is the non-unity feedback systems. Here R of S representing the input and C of S representing the output, and EAS representing the actuating signal, and G of S is the combined transfer function of the transducer controller and the plant, and h of s here is the scaled value of the transfer function in the feedback. So if we want to make it non-unity to unity feedback, okay, it is our task to find the unity feedback systems from the non-unity feedback system. So this case is very simple. If we add a plus feedback and a negative feedback, if we take the plus feedback and the negative feedback, and this negative feedback and combination of both is 0, so there is no difference. But if we take the these two transfer function in a combined way, because both are summing here with negative sign, so next we have hfs minus 1. So there is a only this feedback system, and we have to find the transfer function of this diagram, and this is a simple case we already derived in a block diagram reduction, and there are other many topics we already covered, how to find the transfer function if the open loop transfer function and the feedback transfer function is given. So if we find the transfer function of this one, okay, there are two loops, one is inner loop and other is outer loop. So inner loop, if we reduce into a some closed loop transfer function, then we have only outer loop with positive one feedback, it means unity feedback systems. How to find this one? uh, let's we have a transfer function of this situation is equal to g of s over 1 plus g of s times h of s minus g of s, and here plus 1 transfer function, here is plus 1, no, this is the unity feedback systems. So in this way we find the transfer function for non-unity feedback systems. We have to reduce into a unity feedback systems, just taking the some tricks, and no, this is the unity feedback systems, and this unity feedback systems is treated as earlier, and no, here this E s representing the error signal, because this E of s representing the difference between the R of s, this is representing the R of s, and here is the output value C of s. So this is representing the input minus output. Okay, before going to the next step, first of all we have reviews the topic by using this example. For example, original system is given where this is the G of s and this is the H of s, and this is the non-unity feedback systems. We have to find the steady state error and the system type, which is, and the error constants associated with the system type uh, in this diagram by using the techniques as we derived earlier. So g of s is equal to 100 over s times s plus 10, and h of s representing only a single pole. So okay, in this example we have g of s is equal to 10 over s times s plus 1. Originally, when we are talking about the non-unity feedback, there is this type of transfer function representing, this is the type 1 systems, and h of s is the feedback transfer function, which is equal to 1 over s plus 5. And what happen if we make it in a unity feedback systems. And we drive in the last case that if there is some input RFS, like if we have a RFS and this is the GFS, and here is the C value, and for non-unity case, if it is the feedback transfer function which is h of s negative feedback, then if we want to make it a just the unity feedback, we have to take the output -1 and similarly another value is again here is +1 value, and this h of s and -1 value, if we adding both value, then it is h of s -1 value, and the whole this is the h of s -1 value. And if we want to find the transfer function of this one, then g sub e of s is equal to, originally it is equal to g of s over 1 plus g times h of s, but in our case it is h minus 1. So this is the transfer function for unity feedback systems. So in this case, if we using the transfer function of the original g of s and the h of s, actually if we going to the depth of the definition, g of s, as we discussed in the last few slides, that g of s representing the transducers, controller and plant's transfer function. It is a combination of this one, and h of s representing the non-unity feedback transfer function. So this is the transfer function of open loop transfer function when there is a unity feedback. And by substituting the values of g of s and h of s, we have it is 100 times s plus 5, or and by multiplying these terms we have the s raised to the power 3 and plus 15 s raised to the power 2 minus 50 s minus 4, and this term shows that there is no pole at the origin, as originally there is a type 1 systems, but this is the type 0 systems. If it is the type 0 systems, then it is relevant to the concept of position constants. So we can apply the definition of position constants like position constant is g of s, it is a DC value of this one, and by substituting the values of s equal to 0, it is 500 divided by the 400 and gives the some minus sign here. And steady state error relevant to the position constant is equal to reciprocal of the 1 over 1 plus kp, and kp is given by this one, and steady state error is -4, and this -4 shows that the steady state error values is higher than the input value. Input, if there is okay, definitely by use, if there is a type 0 systems, then it is relevant to the position constant, and we are considering the step input. and usually step input value comparing by this one, and this negative sign shows that if there is a original value is like this one, and by passing through the controller this is equal to this one, it means error values is higher than the input value.
To find the steady state error for non-unity feedback, and also there is some unwanted or disturbances here. So this is slightly tricky. We can handle it in different ways, but in chapter 5 we see that if there are two input for the same systems, for example in this case RFS and DFS are the two inputs, and our course is linear control systems, and definitely here we are talking about the LTI systems. So if the system is LTI, then we can apply the property of this system's superposition. We can apply here. If we switch off one input for one time and solve the whole relation, and similarly if we switch on this input value RS and switch on the DSF. So, and by combining both relations for the output, we find that we have uh, like this one. So this output value is achieved, this part is achieved when disturbance is 0, and similarly this part can be achieved when R of S is equal to 0. So whole this relation is we can use to find the steady state error by substituting this CF this output value which is derived, and the error signal becomes this one, and after applying the final value theorem we can find the steady state. So this error signal is helpful to find the steady state error by applying the final value theorem, and I'm just go through these relations in a quick way. You can drive by yourself. So by applying the final value theorem, and for example if we consider some specific input, for example we are talking about some fixed value of input is the step input, and both for the disturbance and for the reference value. So this case becomes like this one, and this in this situation this S is cancelled out, this S is cancelled out for this reference value as well as for the disturbance. So steady state error becomes this one, and it is a very important concept. We can reduce and we can find the special results from this relation, and this relation is shows that this steady state error becomes 0 if this portion is equal to 1, if this whole value is gives the some unity value, then this portion becomes the 0, and similarly uh, if we take this one is equal to 0, then we have a steady state error equal to 0. So this is another very important result, and it will be we can apply on a different type of problems. Okay, here we have actuating signals E sub A, EA1. So if we want to find the error at this stage due to the existing scenario of the systems, then only just find the error signals here, which is equal to input times G1 by 1 plus G2 H2, and by applying the final value theorem, and we can find the steady state error in this case. If there is one input and one output in a state space or in time representation systems, then we can find the steady state error by using the same previous relations as we tried earlier. So this is the time domain representation, and x representing the state variable, and it is the first derivative is equal to a times x plus b times the input value. Similarly, output is equal to the c times the state variables. And if we apply the Laplace transform, and already we find the output relation is like in this format. So this is the relation we already derived many times. So this is the error signals, and this is the transfer function definition, and like C of S over R of S is equal to T of S. So C of S, if we substitute here, then we have these relations, and this is the closed loop transfer function, and this closed loop transfer functions, if we use directly, then we can't find the error signal by using this relation. So this is the way to find the error signals, and if the error signal is given, then we can apply the final value theorem and find the steady state error. So this is the steady state error relation if the system is representing in state space, and especially when there is one input and one output is related to the system. So if the system is representing in a state space, and for example we are going to implement these result on an example, we have to find the steady state error for the given systems when using the step input and the unit ramp. So for example, here is the system information A matrix, it is 3 by 3, and it is B matrix and C matrix as given. Then we can find the closed loop transfer function from, if the system is given in state space representation, then this is, and here this is representing the identity matrix. So by applying these relations, and we have our closed loop transfer function is like this one, s plus 4 by s raised to power 3 plus 6 x square plus 13s plus 12, 20, and it is the type 0 systems, and it is third order systems. So definition of the steady state error is given by this relation, and if we apply this relation here, and then we have like this one, and taking the LCM of this relation, and we have in a simplest way this steady state definition of this steady state error, this one. And when we find this relation, then now we can apply the different type of inputs here, and we can find the steady state error of the given systems. For example, here first of all, if we apply the unit step, then if there is a unit step, then this R of S is 1 over S, and this is cancelled out with this one, and by applying the limit the r term becomes 0 except the 16/20, and answer is some fixed value. So we have some positive error, and which shows that it is less than the systems after responding the input value system value or output is less than the input value. And similarly, if we apply the some unit RAM, which is 1 over s square, so 1 over s square if we are using here, then 1 s is cancelled out by this one, and 1 over s if we apply the limit, now this becomes infinite, and now we have a infinite steady state error for unit input. In this lecture we cover the steady state error if the information is given in terms of a system information. For example, there is some constant are given, then how we can use these system information to evaluate the systems, and also how to design the values of the especially proportional controller if the some specific information is given. And we extensively find the some relations here, for example steady state error for disturbance, and similarly for the if, and again we are normally talking about the unity feedback systems, but if the feedback is not unity, how to find the steady state error, we handle it. And we combine both the concept disturbances and the unity feedback, and we also drive the steady state error for the specific case. And also we discuss the steady state error in a more specific way, that if we have some uh, system information is represented in a time domain, how to find the steady state error. And just use the closed loop transfer function, which is already derived many times in the course, by the given information of state space, and then substitute into a normal relation and find the error signal, and from the error signal find the steady state error. Hopefully this will be helpful to review the and to understand the concepts related to the steady state error. Try to solve uh, and first of all drive these relations, and then apply these drive relations on different type of examples, and find results. And if you have any query, then you can directly email to me, or you can text me or message me through CR. Okay, thank you so much.